Chapter 6, Lesson 1, Relations and Function. Today we're going to talk about and knock out a bunch of vocab. We're going to talk about function, input, output, and talk again about ordered pairs. And we'll be able to identify functions. And we'll be doing a lot with this standard here. It's going to be similar to the previous chapter we were just in, so it'll kind of sound familiar to us, and we're going to kind of talk about that. To start with, we talk about the input. It is the first element in the ordered pair. So when we talk about an ordered pair, this would be the X value. And notice how it starts with the word in. So it's what we put into an equation. It's what you put into a function. It's what we put in. Then the output starts with the out. It's what we get out of the function, or it's the second thing, the second element in an ordered pair, which means this guy, the output, is another word for the Y value. You're going to see us talk about that. We're going to talk about the input. That's our X value that we put into a function, that we put into an equation. The output would be the Y value, what we get with the equation. A relation is a set of ordered pairs. And a function, this is what we're going to talk a lot about today. We're going to talk about a function, and it's going to have each input to have exactly one output. And we'll see that as we look at it here with some examples, but that's the big thing we need. And then you can see our phrase here. We've got a mapping diagram. It's a visual picture of a relation. It maps from the input to the output. So down here, bottom of your notes, you can see that's what we've got going on here. Right away, right here, these are a bunch of ordered pairs. That makes this whole column here, everything here, a relation. All those points are a relation because they're a set of ordered pairs. And then over here, this is what a mapping diagram looks like. Notice how every input is mapped or connected to its output. So the inputs, these came from these ordered pairs over here. Notice how the ordered pair had an input of 0, an X value of 0, and then that output, the Y value of 1. So you just list all of those going down. You list them in numerical order, and then you connect them via arrows. Up first, it says list the ordered pairs shown in the mapping diagram. So when I look at the input 2, that is follow the arrow, connected to a 1. So the ordered pair is 2, 1. Then you've got the ordered pair 4, 2. Again, just following our input. In this case, the 6 is mapped to, it's connected to the 3, and the 8 to the 4. That one most people would agree with is nice. It's neat. The arrows go straight across. You can see very clearly, whereas over here on the right, same thing, match them up. Just follow the arrows through the chaos. The 1 is connected with the 4. The 2, it has 2 arrows, so follow the first one. It's connected to -5, and then 2 is also connected to 0, and then 3 is connected to a -6. Notice all those arrows. Notice again, when we're looking at these, all of the inputs are listed in numerical order from top down, and the same thing with the outputs. All the outputs are listed here, and I'll move this line slightly so you can see it again. They're listed in numerical order. Think about North Dakota in winter, where the negative numbers, the further from 0 they are, the lower they are, or the colder they are. The closer they get to 0, the warmer it is, and then above 0 gets even warmer. Now, we're going to talk about these and talk about ordered pairs and whether they make or represent a function. So again, you can see we've talked about input and outputs. We talked about our ordered pairs. And now we're going to go talk about if they are a function or not. We'll be able to identify a function from a set of values or from our diagram. So tell that each function, each relation is a function. In order to be a function, each input has to have exactly one output. On the previous slide, that was kind of nice and I don't want to say easy to see, but it was nice here because we see the input 2, that has exactly one output. The input of 4 has exactly one output. 6, exactly one output. 8, exactly one output. That is a function. Every input has to have only one arrow or line coming from it. So when we're looking here, the 1 has exactly one output. The 2, however, has 2 arrows, 2 lines coming from it. That means that the input 2 does not have exactly one output, so it's not a function. That's what we're looking at. When we're looking here, does every input have exactly one output? Does the 0 only have one arrow? Yep. Does the 1 only have one arrow, one output? Yes. Does the 2 have only one arrow, only one output? No. Is that first one a function then? No. Explain your reasoning. You just tell me like the definition said. But in this case, every output does not have exactly one input. That's it. That's all we do. Over here, this is where we have to be careful. We see some duplicates here in the output, but we're only concerned about the input. Does the input -2 only have one output, one arrow coming out of it? Yes. Does the -1 only have one output, one arrow coming out of it? Yes. Does the 0 only have one output? Yes. Does the 1 have only one output? Yes. Only has one arrow. Does the 2 have one and only one output? Yes. That then means that you can say, yes, this is a function, and why every input has exactly one output. And it doesn't matter if the output only has one number in it. If it only had the number 4 and everybody's arrows pointed to 4, as long as the input only has one arrow, it doesn't matter if they're all pointing to the same output. We're only concerned about the input. Does each input have exactly one line, one arrow coming out of it? Consider the mapping diagram below. Is the relation a function? Justify, so we'll say yes or no. Describe the pattern of inputs, and then does it represent a proportional relationship? Justify. Let's take a look down there. Does every input have exactly one output? Looking at the 3, the 4, the 5, and the 6, do they have exactly one arrow, one output? Yes, they do. So then you can quickly do that for part A, yes. And then justifying, every input has exactly one output. Describe the pattern. Now, when it says to describe, just like in real life how you and I could describe the same event differently, there's not really one choice. When I look at this, oftentimes what we talk about is, what do you notice about the input? How does the input change each time? How does our x value change? It changes by 1. So I would say as input increases or goes up 1, the output, well, how does the output change? What's going up with the output? What does it go up each time? How is it changing? What is its pattern? Well, that's going up 12. So as input goes up 1, the output goes up 12. Great. That's one way to explain it. One other way you can look at it is when you just focus in here. How does 3 become 36? How does 4 become 48? How does 5 become 60? How does 6 become 12? You could just tell me the pattern of the inputs is the output is 12 times the input, right? When we're looking at that, 3 times 12, 4 times 12 gives us 48. So you could tell me that the output is 12 times the input. That would be another way to explain it. I'm sure if we wanted to take time, we could find a third way to explain it, but we won't. Does the relationship represent a proportional relationship? Justify. There were two things it had to be. Remember, we talked about it before. It had to be a straight line. Well, you put a check mark by that. We already said all the x's are going up the same amount. They're going up 1 each time. And all of the y's, or the outputs, are going up by the same. Number 2, it had to go through the origin. There were two things. Had to be a line through the origin. Now, I don't see it graphed. You could graph it. I don't see the point 0, 0, or the origin, but let's go backwards. What would the previous point be before 3? It would be 2, and the previous point before 36 would be 24. Go back again, you get 1 and 12, and back again, and you get 0 and 0. So yes, we do get to the origin. So it says, does the relation represent a proportional relationship? Is it very directly? Does it have a direct variation? You can say yes then to this one. And justifying, you just say what it is. It's a straight line through the origin. So that works. That is your reasoning. That is your justification. As you're looking at it, that's what we're doing today, talking about functions, talking about inputs and outputs, about ordered pairs, and talking about being able to identify functions and determining inputs and outputs for functions. That's what we're looking at today. We want to be able to say that you can define relations and functions. You can determine whether relations are functions. And then again, when we talk about this word describe, there are many ways to describe the pattern in the mapping diagrams, to describe the relation between the ordered pairs of coordinates. So pick one way to describe it.